All right, 4.2, log functions. All right, so in 2.7, we talked about inverse functions. So log functions are the inverses of exponential functions. Okay, so a log function you're going to see written like this, whereas an exponential, remember, we had this. So, first of all, let's see, is that in this section or in the next one? No, that's in this one, okay. So, when we look at this, we call this exponential form. And logarithms, if you're not familiar with logarithms, a logarithm is an exponent. Okay, a logarithm is just a fancy name for an exponent. So when we talk about this, this is read as y equals the logarithm base b, that's why it's written as a subscript, base b of x. So you read this as logarithm base b of x is y. Okay, so that's how you want to read that. Logarithm base b of x is y, read as. We can always go back and forth between exponential form and log form. So this is going to be logarithm base b of, I guess I should, logarithm base b of x, the way I have it written here, because the log, this is the exponent that we put on this base to get this result. So this is the base, this is the exponent, this is the result. So let's write it like this. Is the same as logarithm base b of x equals y. These are equivalent statements. This is called log form. This is called exponential form. You want to be able to, if you're given this form, you want to be able to write it as this. If you're given this form, you want to be able to write it as that. So for example, if I say 3 squared equals 9, that's the same as saying logarithm base 3 of 9 is 2. Base, exponent, result. Okay? So given logarithm form, you want to be able to write it like this. Given exponential form, you want to be able to write it like this. These are the same thing. Okay? So that's very important when we get to solving exponentials and log equations. Here, first we want to look at the function itself. So remember the exponential graph, we split up into 2 parts. So just like that, we want to split this one up. So this is logarithm base b of x, and this is for b greater than 1. And just like we did before, for b between 0 and 1, we have a different. So just don't get confused here. We're letting y be the function value. And x here, over here, just to match it with this, we're writing it. I guess that is the same. It's the same. So no problem. I thought I had mixed up the variables there. All right, so exponential function, remember, the exponential function looked like this. That was the exponential function. The log function is the inverse of that. It's like this. And remember, inverses were symmetric about this line, y equals x. All right, so this was the exponential function. So notice the 0.01, remember, was always on the exponential function. The inverse will have 1, 0 on it. All right, so this is the log function. Notice the exponential function rises to infinity. This also rises much more slowly to infinity. Remember the things we're interested in again? The domain of the exponential function is the range of its inverse. The range of the exponential function is the domain of its inverse. All right, so if we just look at this part, the domain is 0 to infinity. That was the range of the exponential function. The range of the logarithmic function is negative infinity to positive infinity. That was the domain of the exponential function. Same thing over here. We had the exponential function looking like this. And if we notice again, we have the 0.01 on the exponential graph. Then we know the logarithmic graph. If it is rising up to negative x's, that means it's rising this way. So our graph, just to make sure I get this right. So this comes this way, and it comes like that. So that is this one. Okay, so again, notice inverses. This is the exponential graph for b greater than 1. And again, these pictures are much nicely drawn for you on page 459. Better than I can draw on the board, but these are pretty good. These look pretty much symmetric about the line. Exponential function, log function for b greater than 1. For b between 0 and 1, exponential function is decreasing. Logarithmic function is also decreasing. 1, 0 is on the log graph. 0, 1 is on the exponential graph. Domain of the exponential is the range of the log. The domain of the exponential function is all real numbers. That's the range of the log function. The range of the exponential is 0 to infinity. The domain of the log is 0 to infinity. Increasing, decreasing are pretty obvious. X and Y intercepts are apparent from observation. So you want to be familiar with the difference between the exponential graph and the log graph. Realize they're inverses of one another. Know the difference between b greater than 1 and b less than or equal to 1. Again, the transformations and reflections all hold in the same way that they did when we looked at the exponential. And the domain, increasing, decreasing, and all of that is also nicely listed for you on page 460, all the properties that we just talked about. Domain, range, intercepts, increasing, decreasing are all listed there for you on page 460. Okay, so we want to look at properties of log functions. Okay, so we talked about changing from exponential form to log form. We want to be able to go from this to this and from this to this. So let's look at something like number 14 on page 465. In 4.2, we want to change to log form. So number 14, we are given the cube root of 64 equals 4. And the question is, write each equation in its equivalent logarithmic form. All right, so this, we have to remember our properties of exponents. So here we have to recall what we talked about a little earlier. When we have radicals, we can change them to a fractional exponent. So that's what we want to do with this. This is 64 to the first, right? You can also think of that as 8 squared, but it doesn't really matter. So here we can write that as 64 to the 1/3 equals 4. That's still exponential form. Now, in log form, the base, our b term, is 64. Our exponent, the y is the exponent, is 1/3, and the x value is 4, the result. So when we write this, right, this is the exponent that when I put it on this base, I get this result. Right? Base, exponent, result. Base, exponent, result. So in log form, we're going to say logarithm base 64 of 4 equals 1/3. That's what we're looking for. Okay? So we change the radical to a fractional exponent first. So we could look at it as a base raised to an exponent equals a result, and then use our log form, logarithm base b of x equals y. Just remember, this is the exponent. I think that's sometimes what confuses students, because the word logarithm is on this side, and I told you that logarithm is an exponent, but this is the actual logarithm, right? This is the logarithm or the exponent that if I put it on this base, I get this result. And that's what we did here. Okay, let's see. I should do another one of those. I think we're good there. Well, let's do one more. 5 to the -3rd. Okay, so same question here. We want to write this in log form. Hopefully, after you see a couple of these are really pretty straightforward. We're saying the base here is 5, the result is 1/125, and the exponent is -3. Okay? And maybe we should take one in the other direction. Let's say logarithm base 1/2, 3. Okay, so something like this. If you're asked to write this in exponential form, again, base, exponent, result. So write this as base of 1/2 raised to an exponent of 3 gives us a result of 1/8. Okay, so be able to change from log form to exponential form, be able to change from exponential form to log form. Know the difference between the exponential and the log graphs, realize they're inverses of one another, know the difference between b being greater than 1, or between 0 and 1 for both the exponentials and the logarithms. All right, so also in this section, we are looking at 4.2, right? We're still in 4.2. Okay, so evaluating log functions. So we've done the graph, we've looked at the difference between exponential and log form. So just like we were evaluating exponential functions, just like evaluating any other function, nothing really new here. Let's look at where's a good log function? Here we go. Okay, so evaluating a log function. Okay, this is just like evaluating any function, just happens to have a logarithmic expression in it. So I'm looking at number 114 on page 467. And this is a function that gives the adult height attained by a female who is x years old. Okay, so this is the function f of x. X is years old. And we're only using x's from 5 to 15, right? Because it's generally only going to be accurate in those age groups, this function. So our function is 62 plus 35 times the log x minus 4. Okay, now something else I didn't mention that I should mention here is when we see something like this and you don't see a base written on the log, if no base is shown, then it's base 10. It's one of the more common bases. No base is shown, then B is 10, which is the button on your calculator. Okay, we have two buttons on our calculators to deal with logarithms. LOG on your calculator is log base 10. So when you don't see a base on a log, it's base 10. The LOG button on your calculator is log base 10. LN is log base E. We talked about that letter E. So when you see this LN, it's a logarithm with a base of E, and that button should be on your calculator also. So we're going to learn how to change any base to these in either this section or the next, because these are the only two we have on our calculators. Okay? This is called a common logarithm, the base 10, and this is called the natural log. Okay, those are the two most common ones. So when we see this, this is what reminded me of it here, there's no base written, so we know that's base 10. Okay? So x is the years old, and f of x is the height attained at age x. And we are asked to evaluate this function. This is the percentage of height attained. Percentage of your total height that you attain at a certain age. And you could read this again, number 114. Okay, so the question is approximately what percentage of her adult height has a girl attained at age 10? So all we're doing here, question basically is, what is f of 10? That's all it is. And we're just plugging 10 into this function. So 10 minus 4. Okay. So logarithm of 6, so we get 62 plus 35 times logarithm base 10 of 6. And you're just going to plug that into your calculator. Logarithm, you're going to hit the LOG button and 6 and get a number for this. You're going to multiply it by 35. You're going to add 62 to it, and you're going to see that you come out with 89.2. So that is the percentage of height attained at age 10, almost 90%. And that's evaluating a logarithmic function, just like evaluating any other function. Again, the only buttons we have are log base 10 and log base E. If it's anything other than that, we are going to figure out how to do that in the next section, 4.3. All right, so what else we got here? 4.2, we talked about evaluating log functions, 30, 32. Okay, let's look at these. So this is evaluating a log function. This is evaluating log expressions. Okay, so this is taking the rule that we just looked at about log to exponential form and using that to evaluate some log expression. So let's look at a couple of these. This is number 30 on page 466. We are asked to evaluate this expression. This is a logarithmic expression. We want to use the properties that we've just discussed to see if we can simplify that down and get a number. So, remember we said, when we see this, That means the same thing as a base of b raised to an exponent of y equals x. So we're saying, what is this? We want to know what that expression is. Well, we know the base is 6. And we can change that radical to a fractional exponent, right? So we use our properties of rational exponents. We know there's a 2 here. There's a 1 here. We don't see those when it's a square root or it's an exponent of 1. But we know we can write this as logarithm base 6 of 6 to the 1/2. Okay, now this is a very nice property that we like to see whenever we see logarithm base b of b raised to something. It's just that something. Okay, so this is a very nice, friendly property. We use this a lot. Okay, we want to create this situation whenever we can. We've done that here. Base 6, exponent is 1/2. So our answer is 1/2. So we had to remember our fractional exponent to radical rule here. And that's important. Remember what we're talking about, exponential functions, logarithms are exponents. So you've got to be really good at your laws of exponents, your properties of exponents. They come up again and again and again and again and again. So similarly to this one, let's say logarithm base 3 of 1 over the square root of 3. Again, we're going to use the same idea. So we want to write this as 3 raised to something, right? So the properties we have to recall are again, the same one we just used for radicals, and also for something in a denominator, right? So using those two properties of exponents, which we all remember well, we can rewrite the term in the parentheses. First, I'll do it in steps. Right? So we got 1 over 3 to the 1/2. Right, using this rule for the square root of 3. And then we're going to use this rule. 1 over 3 to the 1/2 is 3 to the negative 1/2. So we get logarithm base 3 of 3 to the negative 1/2. And now we've got exactly what we want. When this number matches the base here, our answer to this is just whatever that exponent is, in this case, negative 1/2. Okay, so you want to, it's a very friendly formula. Once we get to this point, we just see the answer right in front of us, just like we did here. All right, we still got one more thing here. In 4.2, we have talked about properties. 457, did we talk about? Yes, we talked about that. Okay, so we just mentioned that special property, so let's list a couple of other special properties. The one we just looked at is probably the most used. Whenever we get that. Now, these next ones are sort of special cases of this. If I say logarithm base b of b, and there is no exponent, we know the exponent is 1, so that's just going to be 1. If we have logarithm base b of 1, no matter what the base is, we're saying what exponent do we put on any base to get 1, that's always going to be 0. Right? So these are special cases. So just want to remember those, couple simple examples of that. If I say, what is the logarithm base 17 of 1? Doesn't matter what the base is, it's always going to be 0 if this number is 1. If I say, what is the logarithm base 13 of 13? That's always going to be 1 if the base, if these two numbers are the same. And there's an exponent of 1 here, right? So it's really just this property with an exponent of 1. All right, what else? We talked about the graphs, we talked about domain of the log function, and we talked about common and natural logs. So I believe that's good for this one.